Hi, I'm Hemang Chawla, and I'm pleased to present our work on image masking for robust self-supervised monocular depth estimation, along with Kishan Jeevishwaran, Ilahi Arani, and Behram Zonos. Depth estimation is an essential component of vision systems that capture 3D scene structure for mobile robots, self-driving cars, and augmented reality. Several self-supervised methods have been proposed that predict depth and odometry simultaneously while focusing on reducing error on independent and identically distributed test data. However, the deployment requires a focus on the generalizability and robustness of models beyond performance under ideal conditions, including robustness to natural corruptions and adversarial attacks. Recently, MTSFM Learner showed that the transformer architecture for self-supervised depth estimation results in higher robustness to image corruptions as well as against adversarial attacks by using global context of the scene for predictions. This is unlike convolutional neural networks that have a limited receptive field. Since the performance and robustness of the models are determined by the learned representations, influencing the encoding of features could lead to more robust estimations. We hypothesize that integrating masked image modeling, MIM, into the training of depth estimation would result in learning features that make the model more robust by modeling the global context in a better way. Masked image modeling, or MIM, is a technique that has been used until now for self-supervised representation learning in pre-training of image transformers. MIM pre-training involves masking a portion of image patches and then using the unmasked portions to predict the masked input or its features. It models long-range dependencies and focuses on the low-frequency details present in the images. Two of the popular masked image modeling pre-training techniques, BEIT, which uses blockwise masking, and SIMIM, which uses random masking, can be seen here. We hypothesize that adapting masked image modeling for direct training of a task, such as depth estimation, could lead to richer learned representations that make the model more robust. We examined how MIM can be integrated with depth estimation training and if it would improve robustness of depth estimation. We also examined questions related to the masking strategy to be used, the mask ratio and the mask size, and how the loss should be applied when integrating MIM to depth estimation. We propose our method MIMDepth that trains the depth estimation network by masking a portion of the input to the transformer network while it learns to predict complete pixel-wise depth from the partial observations, including for the masked portions. The input to the depth network is a target image for which the depth is to be predicted, and the input to the ego motion estimation network is a pair of source and target images for which the translation and rotation is to be predicted. The predicted depth and ego motion are linked together via the perspective projection transform for a given set of camera intrinsics, through which the source image is warped to synthesize the target image. Finally, the loss is applied between the synthesized and the original target image for training. For MIMDepth, we utilize the blockwise masking in depth estimation due to its better performance than the random masking. For blockwise masking, a block with a random aspect ratio is repeatedly selected to be masked in the image until the required mask ratio is achieved throughout the image. The indexes to be masked are replaced with learnable mask token embeddings, which are initialized as Gaussian noise for training. Through our ablation study, we find that MIMDepth performs better with blockwise masking applied only to the depth estimation network with no masking on the ego motion estimation. While MIM pre-training in existing works utilizes a high mask size or mask ratio, MIMDepth works better with a relatively lower mask size and mask ratio, and the training loss must be applied only on the complete image rather than just the masked regions to result in better performance. We demonstrate that MIMDepth is indeed able to improve the robustness of depth estimation to natural corruptions, including noise, blur, weather conditions, and digital aberrations. Further, it is also better at predicting depth in the presence of occlusions. MIMDepth also results in improved robustness to adversarial attacks that try to horizontally or vertically flip the depth predictions. Finally, it is noted that in literature, the accuracy of model is often at odds with robustness. Nevertheless, MIMDepth is able to maintain excellent performance on the clean IID data as well. Here you can observe how MIMDepth outperforms existing methods for depth estimation on clean data as well as with different corruptions and occlusions. In summary, with our proposed method MIMDepth, we demonstrate that applying blockwise masking with a relatively lower mask ratio than MIM pre-training only on the depth estimation network with a loss on the complete image results in improved robustness to natural and digital corruptions, occlusions, as well as untargeted and targeted adversarial attacks. Thank you.